Okay, so hello and welcome everyone to today's live session class on the course of Fundamentals of Protein Chemistry, which is being taken by Professor Shagota Dasgupta of IIT Kharagpur. I am Srijan Sen, and today I will be taking your week 5 live session class and discussing with you a few questions and a few problems which will help you in solving your assignment and the future exams which will be coming up. Okay, Okay, so I am sharing my slides with you. I guess my screen is visible to you all and my voice is also audible enough. So I am starting with the lectures. Okay. So in today's class, we would be discussing about mostly protein and ligand interaction. So previously we have heard a lot about proteins, the ways of isolating proteins, how proteins can be prepared and characterized and purified. So we have talked about this in the previous slides. In today's class, we would be focusing on the protein ligand interaction as to how different small molecules or different proteins are reacting with your protein of interest or a protein of interest, how two proteins are interacting. These ligands can be your small molecules or other proteins as well, which we consider as the ligands. So ligands are those that interact with your proteins, and that actually enhances the different functions of a protein. So binding of ligands to a macromolecule, or you can say the protein. So what did Linus Pauling say at the 25th anniversary of the Institute of Molecular Biology in the University of Oregon? So he said that the secret of life is the molecular recognition, the ability of one molecule to recognize another through weak bonding interaction. So using from this statement, he spoke about the protein ligand interaction, or the protein, or how a ligand interacts with its known molecular recognition site, or recognition site of a particular protein, the sequence which the ligand binds to. So what is mostly important for a protein ligand interaction? It is that the binding is the first step which is necessary for a biological response. So the binding has to be the first step. Now, before the macromolecule can perform a function, they normally must interact with a specific ligand. So for carrying out any kinds of function, like you have seen the example of myoglobin binding, then hemoglobin, so binding to the oxygen, its cognate oxygen. So you can understand that how the binding of a ligand or a small molecule or any cofactor to its macromolecule or the protein, say a substance, actually is necessary for performing of a particular function. Now, for understanding how these protein and ligands, or the macromolecules and the small molecules, are binding, there we must consider a particular equilibria as to how the binding is affected by the different concentration of your ligand and the protein, because this is going to actually affect it, the concentration, as to if the concentration of the ligand and the protein will actually determine the binding affinity, or the binding property of that particular interaction. And then we can experimentally analyze and interpret the binding data and different binding curves. So this is known as the reversible binding of ligands, which is very essential because of the specificity of the ligands and the binding sites. Then there are different models, especially we have the induced fit model, where the ligand binding is often coupled to the conformational changes, which is quite dramatic. And then there is the property which we can call as the cooperativity. So here we have another model which we can call as the cooperativity. So in different multi subunit proteins, like we have hemoglobin, then we have myoglobin, like for these complexes, the different subunits needs to come and join together to give it a particular function. means only when those 4 subunits in the hemoglobin are present, that would be definitely responsible for the increasing the binding to your oxygen, or which we can call as the small molecule. So this is known as the cooperativity. Why cooperative? Because one subunit is cooperatively acting with the other subunit to enhance the binding to the oxygen, and these interactions of your protein and ligand can definitely be regulated depending on how and in what manner you requiring it, by changing, say, the concentration of your macromolecule or the ligands. Now, interaction with the other molecules. Now let us imagine an equation which is your A plus B is in equilibrium to your product, that is your AB. So this is a reversible transient process. Now this molecule binds to a protein. Now, a molecule that binds to a protein is called a ligand. So, ligand is the one that binds to a protein, or you can say a macromolecule. So, these are typically your small molecules, but definitely this need not be a small molecule. There is no such hard and fast rule that it has to be a small molecule. This can be other proteins as well. Like for hemoglobin, there are 4 subunits. So, each subunit is also a protein. That need not be a small molecule, but mostly ligands, what we call ligands, are actually small molecules. Now the site to which this protein, this ligand is actually binding to a protein, or where the ligand binds to a protein, is known as the binding site. Now there are different forces by which this ligand binds to your macromolecule or the recognition site of a protein, that is via the non-covalent forces that mostly dictate the folding of your protein structure, and these allows the interaction to be a bit more transient. Okay, now from A B it goes to AB. So from that we are moving on to P plus L, that is PL, where P is your protein molecule, L is your ligand, and this is your ultimate product. And then we have the equilibrium, where this is the binding affinity and this one is the dissociation constant. Okay, this is the association constant Ka, and this is the dissociation constant. So association constant is the one that determines the association of your protein and ligand, and the dissociation constant is one that determines the breaking of the bond between your protein and the ligand, or different non-covalent forces that we just spoke about. So that is determined by the dissociation constant. Now the kinetics of such a process is described by the association constant Ka and the dissociation constant Kd. Now when we write it down in the equilibrium equation, then we can write it as following, like Ka into the concentration of your protein into concentration of your ligand, which is equal to your dissociation constant into the product concentration. And when we actually apply this equation, we get it as the large Ka, that is your equilibrium constant, the total equilibrium constant of your particular reaction. The entire or the bigger equilibrium constant for the equation will be capital Ka, which is equal to your product concentration divided by your protein concentration and the ligand concentration, which is also equal to your association constant divided by the dissociation constant. Now if you calculate it, you get the capital K equals to your association constant by dissociation constant. So from there you can also tell that so this is the very important equation, and you can expect a few questions from this, like you're given the capital Ka value, and then the equilibrium constant is given, and you're given the association constant, then you have to find the dissociation constant as from that particular problem. Now binding, which we can also understand in the terms of the bound fraction. So for understanding the bound fraction, we consider a term which is theta, which is determined as the fraction of the occupied binding sites. So theta is the amount of sites which are occupied in the protein by your particular ligand. Obviously there are a few vacant sites, not all the sites are actually occupied by your protein, only a few or a particular number of sites are filled depending on the concentration of both your protein and your ligand, you can say that. Now when you calculate it or substitute it, so what is theta actually? It is your bound fraction, so the product concentration divided by your product by a total protein concentration. So in which places your protein are, it is also in the product as well as in your main say substrate. Okay, so the substrate and the product both has your proteins. So the entire protein concentration is your protein ligand concentration, that is your product concentration added to your original protein concentration. So this is the bound fraction. Okay, now when we are substituting this product concentration with the equation, that is KALP, from where we got from this, we got it from here. From this equation we got this one, and then when we place the value over here, what we are getting is theta equals to your ligand concentration divided by your ligand concentration plus 1 by your equilibrium constant. So what is 1 by equilibrium constant? It is 1 by Kd as well, that is your dissociation constant. Okay, so Ka by Kd, so it goes up, so Kd, so the capital Kd value, that is your dissociation constant. Okay, so this is a very nice calculation that will help you in finding out your, when you know a particular concentration of your say ligand, and from there you can calculate how much amount of protein is actually bound or how many sites are actually left behind. So this is also very important calculation, and from there what is the mostly the significance of this one is that you can find the Kd value. So the fraction of bound sites depends on the free ligand concentration and the Kd. So from experimentally you can determine not only the bound fraction or the concentration of your ligand and protein, but also it will help you in finding out the most important or the experimentally analyzed variable that you can call as the Kd or the dissociation constant. That will that is very important for your different calculations and all. So that is the reason you require that Kd value. So from there you can comment on the association of the, or the how tight your protein is bound or the ligand is bound to your protein and all. So that will actually help you out. So experimentally, if the ligand concentration is known, then the Kd value can be determined graphically or via least squares regression. So you can find it out experimentally. And what is one assumption that we are taking over here is the ligand concentration is closely equal to your the substrate where you have taken the initial concentration of your ligand. So say you are taking 10 micromolar or 10 millimolar of your ligand. So here we are considering that it is less, very less used. So therefore it is close to your initial ligand concentration. Now on a graphical analysis, if we try to understand this protein ligand interaction, then P plus L is in equilibrium with your protein or protein ligand, that is the product formation. Now previously we have seen that Ka equals to product concentration divided by P into L concentration. Now Kd is just the reverse of it because Ka is 1 by Kd. So Kd equals to your product concentration into ligand protein concentration into ligand concentration divided by your protein product concentration. Now if we recollect what we had understood over here, that the total protein concentration is this one, then we can tell that the protein concentration equals to P total minus the product concentration into your ligand concentration divided by this. And now when we are plotting this particular graph, where in the x-axis we have the product concentration divided by the ligand concentration, and in the x-axis we have the product concentration, then we get a straight line with a negative slope, where the slope is your minus 1 by Kd. And from here also you can calculate the dissociation constant as well. And the two intercepts are the y-intercept being your product concentration maximum, the maximum product concentration divided by your Kd, and the x-intercept being your product max. Okay, and now when this straight line can be also placed in the form of in the straight line equation, where we have y equals to 1 minus kdx plus your total product concentration divided by your Kd value. So from this we can actually get a lot of variables when one of the following variable is missing. So what we need mostly from a protein ligand interaction is the Kd value, because we have to understand how tightly it is binding, which place it is binding, how many fractions of molecules are actually binding. So these are the different parameters that needs to be understood, and because of that, these interactions or the study of protein ligand interactions has been mostly very important. Now let us understand the thermodynamics behind these protein ligand interactions. So if we can understand that the interaction strength can be expressed as your association constant or the binding constant, and the dissociation constant, which is your Kd, and the association constant being Ka. So your association constant is mostly in units of molar inverse, and your dissociation constant being in molar. Okay, so your association constant is molar inverse and your dissociation constant is molar. So Kd, we have seen that Kd equals to 1 by Ka, or your association constant. So that's where the unit gets just changed. And the interaction is mostly determined by the Gibbs free energy, or the delta G naught. So this we call as the delta G naught, which have units of kilojoule per mole. That is the unit of your energy. Now, we have also studied about a very famous equation of Gibbs-Helmholtz equation, where we have the del G naught equals to del H naught minus T del S naught, where this H is your enthalpy and del S is your entropy. So del S is your entropy, which determines the randomness of the particular macromolecule or that particular complex, and del H is the number of bonds or the interactions that are actually forming. So higher the number of interactions, higher will be your enthalpy, and higher the randomness of the complex, higher will be your del S value. So now when we are placing this equation in your association and the dissociation equilibrium constants, then what we get the equation as delta G naught equals to minus RT ln Ka or RT ln Kd. So just it got reversed. So that's where the negative sign got eliminated. So delta G is minus equals to your RT ln Kd. So, and this equation is very, very important. So there are two equations which are mostly very important. I am pointing them out once again. So the first one is del H equals to del H minus T del S. The second one being your delta G equals to minus RT ln Ka or RT ln Kd. And here RT at 25 degrees centigrade is your 2.48 kilojoule per mole. And you can expect a lot of questions from this equation as well as this equation. And only when the delta G value is your negative, the reaction becomes much more feasible. Okay, now speaking of the significance of this Kd or the Ka values. Now what we can call as a strong binding or a weak binding, because there is a binding we know, but whether it is a strong binding or a weak binding or a moderate binding, we know that it is binding, but how strong, the strength of the bond also needs to be understood. So based on that, there has been literature that suggests that our Kd value, which is less than 10 nanomolar, can be termed as strong binding, whereas the Kd value, which is greater than 10 micromolar, is your weak binding. So from here we can tell that the lower Kd value means higher affinity of protein and ligand. Okay, so whenever the Kd value shows an increase, it means that the binding between them is weak, and when the Kd value goes low, that is, you can get the values in nanomolar or say picomolar range, then the values, we can call that as the strong binding. Okay, now let us discuss a few dissociation constant. This is an table. You need not keep this thing in mind, just for as an example we can understand this. So let us understand. So protein, biotin. So protein is the, avidin is the protein and biotin is the ligand. So it has a Kd value of 10 to the power minus 15. So it is such low, and this is known as the, or this interaction, avidin, streptavidin biotin interaction is known as the strongest interaction known. So this, the Kd value is minus 10 to the power minus 15. Now we have insulin and insulin receptor and the insulin, which has 10 to the power minus 10. molar. Then we have anti-HIV immunoglobulin and the glycoprotein 41, which is present on the HIV-1 surface, and this has 4 into 10 to the power minus 10. Then we have the nickel binding protein, which binds to your nickel ion, that has 10 to the power minus 7. Then we have calmodulin, which binds to your Ca2 plus, which has 3 into 10 to the minus 6. So as we move from the bottom to the top, the binding shows a increase. So lower the Kd value, higher is your uh, binding affinity for the protein and the ligand, or any two interactions. Now there is a graph which is given just below, which speaks of the range in which these interactions actually exist. So you can see that the enzyme substrate is present in the low affinity range, whereas antibody antigen is on a much higher affinity region, and biotin is the strongest uh, affinity, has the strongest affinity. And then there are sequence specific DNA proteins that binds to your DNA, which we can call as the transcription factors. And then we have the typical receptor ligand interaction. So there are different kinds of interactions that occurs, and depending on how we want to design our experiments and all, on that basis we can comment on the binding of these particular two molecules. Now let us talk about the Gibbs energy of binding. So the binding constant can be connected to the Gibbs energy by your delta G equals to your RTLN K or RTLN 1 by KD. So there would be a minus sign over here, or depending on how you are performing the equation, you can even place a minus sign over here. So the sign is totally dependent on how you want to design or how you have actually practiced it. So now the binding constant of Ki equals to 10 to the power minus 9, which corresponds to a Gibbs energy of 53.4 kilojoule per mole at body temperature. And the change in the Ki of one order of magnitude means that a change in the Gibbs free energy of 5.9 kilojoule per mole, or 1.4 kilocalorie per mole. So that much, all those things are not much required. As we need to keep in mind that delta G equals to minus RTLN Ka, which is equals to RTLN Kd. Okay. Now if we get back once again into that binding equation, we have already spoken about it, but once again I am just revising those parts. That we have the binding equation where we have the receptor and the ligand, and we have the association constant and the dissociation constant, and this is the receptor and the ligand that is binding. And then we have the Ka, which is equals to 1 by Kd, which is equals to your the complex concentration divided by your receptor concentration and the ligand concentration. So this is the equilibrium equation which you can which you have already done before. So based on enthalpy and entropy, we know that delta G equals to minus RTLN Ka, which is equals to a delta H minus T delta S. So now when we divide them by T, what we get here is minus delta G by T equals to minus delta H by T plus delta S. So now if you're given these particular values, then you can also frame or you can get the few you can get a question like this for finding the say entropy. Okay, so you are given two or three of these variables, and you have to find another variable. So three variables are unknown, so two are given, so you have to find out one of them. So depending on these, you can find a lot of questions over here. So these are not much difficult, only you have to keep in mind a few equations and you have to understand the fundamental concepts, and only then you can easily solve those questions. Now the important types of protein ligand interactions are basically based on your hydrogen bonds. That can be your typical or untypical hydrogen bonds, charge assisted hydrogen bonding. Then we have the ionic bond. So the interaction has to be performed in a particular manner, or by holding the hands of particular forces or other interactions. So based on that, what are those interactions? The interactions are mostly your hydrogen bonds. Then we have the ionic bonds. Then there are hydrophobic interactions. So these are mostly those interactions that play important role in the folding of your protein, and these important interactions have equal roles, or say equivalent roles, in your protein ligand interaction property as well. And then we have the cation pi interaction. So hydrogen bonds can be typical, untypical, or charge assisted. Your ionic interactions mostly depends on the effect of the pK values of the amino acids or the small molecules that are coming and binding to it, and also it depends on the local pH, the local environment, which the pH which is present in the local environment. So based on that, there are also different interactions that the ionic interactions play an important role. The another important interaction being a hydrophobic interaction. So these are mostly caused by the displacement, and more correctly put, the liberation of water molecules from the lipophilic environment of the binding pocket. So when we have a lot of hydrophobic molecules that comes and clubs together, so these are different non-polar interactions that occurs and that displaces the water molecules. So that is only stated over here, that the water molecules are being displaced, and then via the hydrophobic interactions the two molecules can bind. And then we have the cation and the pi interaction. So the pi interactions are because of the aromatic residues or the aromatic compounds that are present over there, with that binds to the different cofactors, say the divalent cations and also cation and pi interaction. So these can also be important protein-protein interactions. So we need to keep in mind about the four interactions. One is the hydrogen bond, ionic bond, hydrophobic, and the cation pi interactions. Now coming to how can we, now we have till this much we have spoken about the interaction between a protein and a ligand. So we know that the protein or the ligand is binding to your protein, the ligand has a particular equilibrium. These are entirely the theoretical part. Now how can we understand that your protein is actually binding to your ligand? So we have to experimentally determine the binding affinity or the dissociation constant, or how tightly your ligand is binding. So for that there are different, say, tools and techniques that we can use for understanding the binding or affinity of a particular interaction between two molecules. So the first one being your isothermal titration calorimetry. So what is this? So this is a direct, so this is the principle that I am discussing. So this is the apparatus system that is present over here. There is a heating probe, and here we have the proteins and the ligands. So the isothermal titration calorimetry is a direct method. So it measures the heat change that is associated with complex formation at a constant temperature, and complete thermodynamic profile of the molecular interaction can be determined in a single experiment. So you can get the thermodynamic parameters from these experiments. So basically you can find out the enthalpy, the entropy, then from there you can find out the Gibbs free energy, the binding affinity, as well as the stoichiometry of binding, as to how many number of molecules are of the ligand are binding to your protein of your interest. Now these say ITC, or your isothermal titration calorimetry, is mostly involved in calculating the heat. So why does it calculates the heat? When there is when the protein binds to the ligand, there is a liberation of heat. Okay. So from that the heat is being calculated. Okay, and from the heat we can get this following parameters. Now this is the instrument that is present over there, where we have the reference cell, where we have a particular solvent that is that maintains the reference cell, and that we can consider as the standard. And there we have a syringe, which from where we uh, put the sample and the ligand. So this is meant for the constant power to the reference cell heater. So here delta T equals to your 0. There is no change of temperature between these two cells as well. And this is the sample cell. The power supply to the sample cell feedback is important for keeping the delta T to be 0. And this is an adiabatic jacket, So because of that, the temperature remains constant over there, and now we have a reference cell and a sample cell. Now what happens? Okay, so now what happens actually is very interesting. So we have a protein inside this sample cell, and then we are injecting the ligand. Okay, so first thing that we need to keep in mind is that the proteins are present inside the cell, and we are putting the ligand from the syringe. Okay, now the ligands come and interacts with the protein. Okay, now when they come and interact, there can be an endothermic heat event as well as an exothermic heat event. So when there is an exothermic heat event, you get peak values like this. So there is a binding, and then it goes out, and then there is another binding. So based on that, you will see that with time your binding decreases because the number of spaces are already filled up. Okay, so you see, fine, imagine you have 100 protein molecules and 20 ligand molecules. So in the first go, say 5 molecules are binding, so you get a peak, a long peak, and then in the next event there are 4 binding, again there are 4 binding, again there are 4 binding, then there is 3 binding. So the number of the number of ligand molecules are also decreasing from time to time, as well as the number of sites where the ligands can bind is also decreasing over the time. So because of that, you will see that the curve is decreasing in a particular manner, and the same you will observe for the endothermic heat event as well. So this is the entire apparatus which has a sensor, then you have the lead screw, and then we have the injector, the plunger, then we have the starting, the syringe, the outer shield. This one is your sample cell, this one is your reference cell, and then we have the inner shield to give it an adiabatic environment. So what we need to actually keep in mind from these type of experiments is that the first thing is that what can ITC be used for. The second thing is that what values or what parameters can be received from these experiments, or what data can we get from these experiments. And the third thing is the analysis part. So this is very important because we get the thermodynamic parameters from over here, especially the enthalpy, the entropy, then with the stoichiometry can be found out from these ITC experiments. Also it maintains a constant temperature, and the heat that we are actually calculating is very important, and these graph can also be analyzed to find out the binding affinity about the different interactions. Now let us review free energy, enthalpies and entropy of binding, where delta G equals to RTL and KD, where these values are given. Now we have a log relationship between the free energy and the binding constant. Now if we recall that the delta G binding is relative to your standard condition, then we have a convenient rule of thumb, that is a tenfold change in binding constant corresponds to your 1.4 kilocalorie per mole. So how many kilocalorie per mole change in free energy do you need to change KD by 100-fold? So what we so this is a question which you can solve now. Okay, so this is, so for tenfold change in the binding affinity, it corresponds to 1.4 kilocalorie per mole. So 100-fold change in the KD value, it will change the gives free energy by how much. So if you see that it's log 10, that is so 1.4 into your log 10, that is 1.4 kilocalorie per mole, and when you get 100-fold, so that is log 100, that is 2 into 1.4, so you get minus 2.8 kilocalorie per mole. So this is an easy equation calculation. So we have to calculate it on the logarithmic term. So log 10 and log 100 over here. So 1.4 into log 10, and here it is 1.4 into log 100. So log 100 equals to 2 into 2 into 1.4, that is minus 2.8. So therefore from this equation we can also get the particular values, and we have already spoken as to what we can call as a strong interaction. So I'm just repeating it once again. So delta G naught must be large and negative, delta H naught must be large and negative, that is gaining of new bonds. So when there is a new bond formation or a new interaction that is occurring between two atoms and all. So that is actually increasing your delta H, and it is becoming negative, and your delta S must be large and positive. That is, it should have a more entropy, or the randomness should be more. So depending on that, the interaction, we can call a particular interaction to be strong. Okay, coming to another very interesting experiment, which is your SPR, or you can call it as the surface plasmon resonance. It is mostly based on the principle of your total internal reflection. So what is a surface plasmon? So the longitudinal charge density wave along the interface of the two media. So we have two media over here. This is glass, and here is liquid and air, and this one is coated with a metal film. Usually we have a gold foil over here, which actually separates the liquid from the glass, and then there is a polarized light that we are passing over here. And we know that when the angle, the initial angle is incident angle is greater than your critical angle. So critical angle is when you get it, when it's equal to your critical angle, you get along the baseline. But when it is greater than the critical angle, it just uh, performs the phenomenon of total internal reflection. So when we based on this principle, we have a detector placed over here, and from there we get the theta values. So so surface plasmon is your longitudinal charge density wave along the interface of the two media, where one is a metal and the other one is dielectric. So what is the principle behind it? So say you have a particular interaction over here, and this is a linear relationship which is found between your resonance energy and the mass concentration of the biologically relevant molecule. So SPR is excited by a polarized light which is totally internally reflected at the glass or the metal surface. Okay, and the surface plasmon enhancing the field amplitude E. Now which we now there is a core system which we has a sensor plate over here. So there is a sensor over here that actually senses the interaction. Now this interface takes the form of an exchangeable gold coated glass slide. So this one is gold coated, and this is observed as a dip in the reflected light intensity at a specific angle of reflection. And here what we are calculating is the reflected light, or the total internal reflection, and here we have a detector that is actually measuring it. Now where there is an interaction, there would be, now there is a light going here, there is an interaction, imagine it's going over here, so there would be a gap, so you get a peak over here. So this indicates the dip. Now this dip actually at a particular angle determines where the interaction, or in which manner or how complex the interaction is occurring. So okay, now here we have is the polarized light, and here we have the prism, then we have the reflected light that we are actually calculating, and here an interaction is taking place. So this is a sensor chip, and now the bottom layer is your gold plated film. Now in the base of it, there are antibodies, and then we are passing say antigens over here. So first there is a binding that is going on. Okay, so there is a binding. So mostly this graph you will see, you will observe for the SPR experiment. So in the first stage there is a affinity, then there is binding, and after one point it reaches a constant region. So there is binding, 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 and then at one point there is a equilibrium that is reached. Now when the equilibrium is reached, then there is a elution buffer that we pass through over here to elute these molecules from the surface, or the antigens from the antibodies. And now there is a drop of the resonance because the interaction is no longer over there and it is decreasing. So based on this, so now there is affinity, affinity, affinity. Now when depending on the rate of the decrease of the interaction, or the protein ligand that is interacting, we can comment on the dissociation constant, because the tightly the interaction is occurring, the slowly the molecules will dissociate, and if that is a very weak interaction, then the dissociation is very fast. Okay, so the longer the time it takes for the molecules to actually break the bond and dissociate, the tighter the binding affinity is, or the higher the binding affinity is. And the faster the molecules dissociate from an interaction, the interaction is termed as a weak interaction. Now, what are the different? Okay, so another thing I'm just repeating about the SPR protocol and the outer, just the fundamentals of it. So we have a polarized light that goes and strikes the surface, and then the ray is totally internally reflected, which we are actually detecting. Now, on the surface, it is gold plated, and above that, we have a sensor plate. Right. So there is an interaction that is going over there, and we are measuring the interaction. So in the first step, we have the protein that is bound to the surface. We are passing the ligands, and after, so the ligands are binding, and after one point of time when the equilibrium is reached, we pass the elution buffer to dissociate the interaction. Okay. Now, depending on the dissociation of these particular interactions, what we get over here is the dissociation constant, and that's what we are actually calculating. Now, what are the different applications of your SPR? So there are physical applications that measures the dielectric properties, then the adsorption processes, the surface degradation or the hydration of your thin organic monolayers, bilayers, and then you have the polymer films. Also, there are different biological applications that is necessary that you can use as biosensors for the specific biological interactions, which includes your adsorption and the desorption kinetics, the antigen antibody binding, and epitope mapping for the determination of your lipid bilayers, then non-specific biomolecular interactions, biocompatibility. Then we can use them for protein and tissue engineering, also for studying the different biomolecular structures of your proteins, DNA, viruses. So depending on all of these, there are a wide applications of this surface plasma resonance. Now, there are different advantages of your surface plasmon resonance. One is the ability to perform the real-time measurement. So you can see on the screen as to how the binding affinity is occurring and how the dissociation is actually being done. So this is a real-time measurement. You get an insight to the dynamic nature of the binding system and the layer formation. Then you can use selective slides to study the binding events to eliminate the need of labeled reactants is not actually required, because these labeled samples are actually very costly, and some of these samples can be even radioactive. So we are eliminating the use of that labeled reactants, and it is a very highly sensitive. It has exceptional sensitivity, so small quantities of purified reagents will be sufficient to perform these experiments. Also, these experiment has a certain drawbacks or loopholes. So one of them being that the lack of sensitivity when monitoring low molecular weight absorbent. So lower molecular weight proteins are difficult to be performed in these SPR instruments, and the rate limiting factor of the mass transport affecting kinetic analysis. And based on that, these disadvantages, there are other techniques that we can use, one of them being your atomic force microscopy. Means we can couple these SPRs to the atomic force microscopy, and the other thing is that coupling with the mass spectrometry. Okay, so based on these we can also understand the interactions of the low molecular weight proteins as well as the rate limiting factor of the mass transport. So these can be the two solutions of the two problems that has been stated. Another important okay, so another interesting technique over that we have to study is the EMSA. So previously we have studied about ITC and your SPR. Now we are going to study over here is EMSA. that is an electrophoretic mobility shift assay. It is also known as the gel shift assay, where we study the protein DNA interactions. It is a technique where you study interaction of your protein with DNA, protein with RNA, and there are different cellular processes where the protein needs to interact with your DNA and RNA, like your transcription factors, translation, and transcription. Now, these are utilized broadly in investigation of sequence-specific DNA binding proteins, such as your transcription factors, and explore the DNA protein interactions and the RNA protein interactions. And this particular technique is very sensitive, using radio labeled nucleic acids and autoradiography, and it is even possible for very small concentration of your radio labeled DNA and RNA. So what we do over here is the purified protein, and the cell crude extract is usually incubated with your 32p labeled isotope labeled DNA and RNA probe, and the complex and the unbound probe is isolated on the non-denaturing polypropylene gel electrophoresis, or you perform a native or a denaturing or a native gel. Okay. Now, the mobility shift is the electrophoretic separation of a DNA and protein, or the protein RNA mixture on an acrylamide or an agarose gel for a short period. The speed at which the different molecules moves through the gel is determined by the size, charge, and sometimes the shape. Okay. So what you can do over here is that you have a protein and you know a ligand, so you run them on a native page or non-denaturing gel, and they will be running according to their size and all. But when there is a complex formation between the protein and the ligand, they will be running higher than the two particular lengths. So based on that, you can actually comment about the complex formation, and with you will see at different concentrations of protein and ligand that band gets reduced, and the time or the lane in which you understand there is 50% protein, or 50% of the sites of the protein binds to your ligand, and that is you can call as the dissociation constant value. So how and why titration is done? So okay, you can see over here, so as we know that we are going to have the DNA interacting with the protein, and for that to happen we have to have enough DNA and protein in the solution. So this is the titration of a single residue single stranded DNA with a human AGT protein. So you can see there is an interaction over here. So this is the bound fraction and this is the free DNA. Okay, so there is a shift. So you can see in the first lane you have the bare DNA, then you have protein DNA complex and protein with that, and the DNA that is bound to your two proteins. So you can see that there is a shift. So here you have the DNA, here you have the protein, and there is a you have the protein bound to the DNA complex, and there we have the DNA that is bound to two proteins. So that's why there is a shift. So based on, and you can also see over here that the band is decreasing as the proteins are interacting with your DNA. So from here you can comment on the dissociation constant of the protein. So what are the applications of EMSA? So it is used to understand the conformational changes in the DNA, and this is a 2D experiment which is also good than the electron microscopy, which is used for the characterization of the conformation. It is also used for analyzing the cellular extracts for the presence of certain DNA binding proteins. Bound and free DNA are separated using your EMSA, and it also proves useful for the stoichiometric analysis. Just as I was saying that the 50% of the ligand bound to the protein is the state where your protein, that is called as the dissociation constant of your protein and ligand. Okay, so 50% when it is bound and unbound is where you get the KD value. And also it is used to study the transcription, whether the transcription factor is attached to your DNA or not, or if the transcription factor attached is targeted and up to their activity or not. So these are the theoretical portions and the applications. So mostly what we need to understand, another one time I'm repeating, is why are we using these experiments, what these experiments what data or what results these experiments actually provide us. So that is important, and analyzing of that particular data. The theory is important. The applications plays an important role when you're performing these in the research field, or when you're performing the experiments. We need to keep these things in mind, but the most important is the principle and how we can analyze the data. The advantages of EMSA is that it can be used with wide range of nucleic acid sizes, structure, as well as a wide range of proteins. It is relatively simple method to perform and is used for the qualitative analysis. And it also proves useful in detection of protein that binds to your DNA and causes difficulty in migration of fragment on the gel. It is a very high sensitive method and low cost, so no special equipments are actually required for it. You need to just run a gel. So for that, the basic chemicals that you require is mostly available in any kind of labs, and in this technique it is both possible to use the crude extracts as well as the purified recombinant proteins. So these were the advantages, and these are the few drawbacks of your IMSA. So it does not provide a straightforward measure of the weights of the protein, as mobility is influenced by several other methods. So you do not get an note or an proper, say, a proper data about the molecular weights, and it is very difficult for the kinetic studies of your protein ligand interactions or the protein nucleic acid interaction. So IMSA is mostly for your protein DNA, protein RNA. So these are protein nucleic acid interactions for studying it. So this is another drawback. Okay, so here you can only study about the protein DNA and the protein RNA, about the nucleic acids. And then the dissociation is also one of the drawbacks of IMSA. It occurs during the electrophoresis, thus preventing the detection, and the interacting biomolecules must have different electrophoretic mobility. So based on that, sometimes there might be a uh, misleading data. Okay, so this can be a few drawbacks of this particular experiment. And I guess this is the last experiment for understanding the protein ligand interaction, that is your fluorescence anisotropy experiment. So before that, we need to understand how the polarization is occurring in a fluorescence experiment. So here we have an excitation, and here we are detecting it. So in the x direction we have the excitation, and in the y direction is the detection. So the polarization is P equals to intensity in the parallel range minus intensity in the perpendicular, divided by intensity in parallel plus intensity by perpendicular. So this is the polarization state of fluorescence that is being described. Whereas anisotropy, that is determined by R, equals to your intensity in the parallel range minus intensity in the perpendicular, divided by your total intensity. So anisotropy is preferred because it contains the total intensity. So the total intensity over here is equal to your parallel intensity plus your perpendicular intensity. So why there are two perpendicular intensities? Because it is operating in one direction, okay, and there are other two, means this is the parallel intensity, say you imagine, and in the Z direction you have a perpendicular intensity, and in the Y direction you have a perpendicular intensity. So one parallel in the direction, say X, from the X direction you are operating, so this is the parallel one, these two are the perpendicular. So this is the total intensity. So why is the total intensity equal to? So you see over here that I have mentioned over here, for the reason of symmetry, the component polarized in the x direction and y direction will have the same perpendicular intensity, but in the given geometry we detect only one polarized x direction. So because of that, or you can also imagine in that it has a z direction and the y direction and the parallel intensity as well. So now coming to anisotropy and the molecular motion. So we have considered frozen molecules. However, in reality, the protein molecules are present in the solvent and they have high entropy. Okay, and their rotation changes the orientation of the dipole theta. So changes in the theta are reducing the anisotropy that is caused by photoselection. So RT equals to R naught exponential minus T by rho, where rho is the rotational correlation time. So these equations you need not keep in mind, but just keep in mind about an idea about how this entropy, the principle behind entropy. That much details detailed questions won't be there in your assignments or the questions in the final exam. So for a spherical molecule, your theta equals to viscosity into volume by RT, which equals to 1 by your 6 into translational diffusion coefficient. And for a globular protein, you have this where you have its dependency on the partial specific volume and the degree of hydration. So how are we going to measure the fluorescence intensity? So we have vertical excitation, and here we have the sample, and there we are detecting this particular thing. So the plane is defined by the direction of the excitation, and the detection is called horizontal. Now the measured intensities are identified by two indices. So these are the two indices. One is the analyzer and the polarizer. So the polarizer is the detection channel. So we have to account for the different sensitivities of detection of individual polarizations. So from there we can revise the equation from here to here. Okay, so this is what we have, and the values of these intensities are given over provided over here. So these are the sensitivities in the vertical range and the horizontal range. So G is the measure of, G is a constant that measures the, that is the ratio of your vertical sensitivity divided by your horizontal sensitivity. Now this is time dissolved fluorescence anisotropy, and where we have the scattered light that causes higher anisotropy because it is completely polarized, and it is necessary to minimize scattering for accurate anisotropy measurement. So when you are plotting photon versus channel, you get a peak like this, where this is your vertical versus vertical horizontal, and this is your vertical vertical. And then when you are plotting anisotropy versus the channel, you get a plot like this. You get different kinds of points and slots, and then you design a curve like this. Now polarization methods are ideally suited to study. Now this slide is very important because here we will get the applications of it. So it is usually for studying the aggregation of the states of the proteins. Now if we consider a protein dimer monomer equilibrium, so this is the dimer and this is the equilibrium. So one of them is fluorescently tagged, where we have one with one suitable probe, and one would expect the polarization of the system to decrease upon dissociation of the dimer into monomers, because when they are in dissociation, when they are in association, it will be fluorescently glowing up, whereas when they are dissociated, the intensity of the fluorescent just decreases. So decreases upon dissociation of the dimer, since the smaller monomers will rotate more rapidly than the dimer. So there will be low intensity that you will be calculating. So this is lower P and this is higher P. So hence for a given probe lifetime, the polarization or anisotropy of the monomer will be less than that for a dimer. And based on that we can, because there are molecules that are more flexible and they are in the mobile phase, or they have high entropy. So when the entropy is very high, so the detection patterns will somewhat get reduced when they are monomer, because they are always in a very random state. So for catching up that intensity, it becomes difficult. But when it is in a dimer state, it becomes a lot more compact, or when it forms a lot more polymers, it becomes a lot more compact, and then calculating the, say, your intensity becomes much more easy, and then you get higher peaks. So the intensity for our the intensity for our dimer is, so the intensity for a dimer is much higher than that for a monomer, right? So I think that much was with the theory portion, where we had studied about the different interactions and what were actually responsible uh, forces that are responsible for the different protein ligand interactions. Then we studied about the four techniques, important techniques. One is your ITC, that measures the heat. and from there you can calculate the thermodynamic parameters. Then we have the SPR, which from where we can also get a few data about the interactions. Then we have studied about IMSA, which is also important for your protein, DNA, RNA interaction, nucleic acid interaction. And lastly, we discussed about the fluorescence anisotropy technique. Okay. Now we will be solving a few questions. So you people would be answering me, and then I will be discussing with you the answers. Okay, so you can answer me in the chat box from where I will be taking over. Just a minute. Yes. So, okay. So let us start with the first question. The dissociation constant has a unit of. These are direct questions. Okay, so you say B. Just a minute. The dissociation constant has a unit of. No, it is not B. As I was speaking, the association constant has a unit of molar minus 1 or molar inverse. So dissociation constant is only its concentration, not concentration by time. So the correct answer would be your A. Okay, the next question. Electrophoretic mobility shift assay is a technique for studying DNA protein interaction. It is performed using. So what can we use for studying IMSA? Is it agarose gel, native gel, SDS or urea polyacrylamide gel? I just discussed about it. I think that's no. It is not an agarose gel. It is a native polyacrylamide gel. Because as I was speaking, that it has to be a denaturing polyacrylamide gel where you will be running the protein, you will be running the DNA. It's not about separately the protein and the DNA that we are running. It is the protein DNA complex that we want to study. Yes, we can see the DNA even in denaturing condition. Okay, so remember this. So for studying the IMSA, we have to run a native gel, and this native gel is a non-denaturing gel where we do not have any detergent or cationic or anionic detergents. Like for SDS page, we have a anionic detergent that gives a negative charge, but here we want to have that charge by itself, and then we have to study the complex formation. Okay, so it's a native polyacrylamide gel. Okay, never mind. The next question. Which of the following experiments can be used to determine the binding kinetics under favorable conditions? So which of these experiments can you perform? And this is a multiple choice question. Means, sorry, this is an MSQ question. So more than one option can be correct. So for studying the binding kinetics, which of the following can you use? So if you see that for studying the binding kinetics, so there is always a difficulty for studying the binding kinetics for the case of IMSA, but for any other technique you can always use it. So it is B, C and D. But for IMSA it is difficult to study the binding kinetics. So B, C and D are the correct answer for this question, where we have to study the binding kinetics. Okay, the next question. Enthalpy of a binding reaction can be determined from. So enthalpy can be calculated from which experiment? So from which experiment can you calculate the thermodynamic parameters? The enthalpy is a thermodynamic parameter. So from which experiment can you do that? So if you see and get back to my slide, it is the ITC experiment, or the isothermal titration calorimetry, from where you get the thermodynamic parameter data. Okay, so A is the correct answer. So free energy of a binding reaction can be determined from. So the free energy of a binding reaction can be determined from which experiment, or from which experiments? You say it's sorry, just a minute. Okay, you are saying it is D. Yes, you can get it from D, that is also correct. Any other experiment from where you can get the free energy? Definitely you can get the free energy from ITC, because it is a thermodynamic parameter. Any other experiment? Actually, if you see that the free energy of the binding reaction, that is delta G, equals to RTL and KD. So the KD value you can get from all of these experiments. So therefore you can get the free energy also from all of these experiments. So A, B, C, D, all of the four are correct options. Okay. The next question is surface plasmon resonance detects. What does this SPR experiment detect? The change in heat after ligand is added to the protein, the change in refractive index of the medium near the sensor chip, the change in migration of the protein ligand complex, or the change in the viscous drag. What is it? No, the change in the heat after ligand is added to the protein is for ITC, but it is the change in the refractive index of the medium near the sensor chip. As I was speaking, it has a gold foil on that, then there is a sensor chip on that actually helps in the detection, that senses. So surface plasmon resonance is for measuring the change in the refractive index of the medium. These are the questions which you can expect in your assignments as well as your exam. So be careful with these questions, because I understand that the techniques are a bit tricky, but you have to keep these things in mind. Okay. Now the next thing, in a fluorescence anisotropy experiment, a small ligand is stacked with a fluorescent label. Which of the following is true? Increase in rotational diffusion of the small molecule is detected. Decrease in rotational diffusion of the small molecule is detected. The fluorescent level is excited by the polarized light. The fluorescence level is excited by the depolarized light. Okay, that is correct. The fluorescent level is excited by the polarized light. And any other option that is correct? Another option that is correct is the decrease in the rotational diffusion of the small molecule is detected. So as I was speaking, there is a loss in the intensity. Okay, or there is an increase in the intensity when it is binding. So the decrease means the molecule is no longer in the mobile state, or the entropy is not that much high. So there is a decrease in the rotational diffusion of the small molecule. Right. Okay. Now another question. A protein binds a ligand with an association constant 10 to the power 6 molar inverse. What is the most likely measured Kd in the presence of a competing inhibitor? So keep one thing in mind, there is the presence of a competing inhibitor that will inhibit your association. So when something is competing and it is competing as an inhibitor, so what do you see? So the thing that occurs is that when it is competing, the association will ultimately decrease and the dissociation constant value will be higher. So a higher dissociation constant value means it will be Kd, that is 10 to the power minus 5 molar, because it is 10 to the power 6. So 1 by 10 to the power 6 is 10 to the power minus 6, but as it is in the presence of a competing inhibitor, it will be 10 to the power minus 5 because the value is increasing in the presence of a competing inhibitor, right? Okay. Now from the dissociation constant it is possible to calculate. So what can you calculate from the dissociation constant value? The association constant, the delta G, the concentration of the ligand required for the half maximal occupancy, or the binding and the dissociation rates. So what can you calculate from the Kd value? It is also an MSQ, so more than one option can be correct. Think before you're answering. Just think before you give an answer. See, when you have the dissociation constant, you will definitely can calculate the association constant. The delta G also can be calculated because delta G equals to RTL and KD. And also from the KD, I was speaking that concentration of protein into concentration of ligand divided by your complex concentration. So the concentration of the ligand can also be calculated, but this one is not true. The kinetics cannot be calculated. So A, B, C are correct, but not D. Okay, now in a titration experiment to determine the dissociation constant, what is important in a titration experiment? So it is saying in a titration experiment, the ligand concentration is varied and the protein concentration is kept constant. That is right. So this is the correct answer. Okay. The next one is saying the ligand concentration is kept constant and the protein concentration is varied. That can also be true, because if you have the ligand in the cell and then you are titrating against the protein, that is also true. And the next one is it is necessary to determine the concentration of the free ligand, free protein and the bound complex, and it is necessary to keep the temperature constant. C is not correct, but D is correct because we do it in an adiabatic environment. Okay, the next question. Electrophoretic, and you can get all of these after you listen to the lectures, as well as if you can follow my slides, you will be getting all of these answers. So for the time being, I'm just discussing them, but try to answer them on your own. This will also help you. Now when you will be solving the assignments, you will come across different questions as well. Okay, the next one is the electrophoretic mobility shift assay is used to study. What is EMSA used to study? This is an easy question, and you should give me a quick answer. Protein small molecule, protein nucleic acid, protein polysaccharide. So EMSA is used for studying protein nucleic acid interaction. Protein DNA, protein RNA, mostly this. Okay, the protein ligand complex dissociates with an off rate of 1000 second inverse. What is the time constant for this reaction? So it is nothing, just what is the time constant? Tau equals to 1 by k of, that is 1 by 1000 seconds. So where we have seconds, so here we have second but not 1000. So 1 milliseconds. Okay, 1 10 to the power minus 3 because 1 by, so it is ultimately 1 divided by this. So 1 millisecond is the right answer. Okay, the next question. The expected k of rate of a protein is 100 second inverse. Which of the following true, or which of the following is true for studying the kinetics of the reaction? So data should be collected at every 4 millisecond or faster. Data should be collected for at least 40 milliseconds or longer. Data should be collected at every 40 seconds or faster, and data should be collected for at least 400 seconds or longer. So you see here we have only the k of value, that is 100 second inverse. So the correct answer to this would be the data should be collected at, because this is an experimental design. So the data should be collected at every 4 milliseconds or faster, and data should be collected for at least 40 milliseconds or longer. So these two are the correct answers. Okay, so this is an experimental design. You need not get this question. Okay. So for protein ligand interaction described above, which experiments are suitable for the study of kinetics? So again going back, which experiments can you use for the kinetic studies for protein ligand interaction? So just it is protein ligand interaction only to study the kinetics. Or where can you see for the real time? Where can you study the real time kinetics? No, it is not right. Isothermal titration calorimetry is not correct. It is actually surface plasmon resonance. Okay, so this is for the uh, for studying the kinetics. Okay. Now the next question. Ligand A and B binds to a protein P with dissociation constant 1 nanomolar and 100 nanomolar. Which of the following is true? A binds P more tightly, B binds P more tightly, A has faster off rate, B has faster off rate. See, A binds with P with 1 nanomolar, B binds with P with 100 nanomolar. So which binds which one more tightly? Because nothing is given about the kinetics, so we cannot tell anything about the off rates. So C and D are not correct, but lower the KD value, higher is the affinity. So A binds P more tightly will be correct. Okay. Now coming to a similar type of a question. Ligand A and B binds to a protein with dissociation rate constant 0.001 second inverse and 0.1 second inverse. For A and B, association rate constant are 10 to the power 4 and 10 to the power 7. Which of the following is true? So first, if you see from the association rate constant, it is 10 to the power 4 and 10 to the power 7. So higher the association constant, higher will be the binding. So B binds P more tightly. That is correct. Now coming to the off rate, from where you can, so the on rate can be used to tell about the tighter binding, and the off rate can be used to speak about the longevity of the two complexes. So the off rate is 0.001 second inverse and 0.1 second inverse. So if you divide it one by this, one by this, so it is 1000 seconds and it is 10 seconds. So higher the or lower the k of value, higher will be the longevity. Okay, so therefore this value is low and this is higher. So A binds to P with the lower k of, and B binds with P with the higher k of. So AP complex is higher or longer lived. So B and C are correct. So from K on or from the association constant, you can tell about the binding affinity or the binding of the how tightly the complex is forming, and from the K of you can tell about the longevity of the two proteins as to, because if it is dissociating very slowly it is longer lived, and if it is dissociating faster it is less long lived. Okay. Now coming to the last question, the dissociation rate constant for a protein DNA interaction is determined by EMSA. The intensity of the free ligand can be fit to which of the following equation to obtain K of. So this equation is actually you have to keep in mind, and I am just giving an answer to this question. So the answer to this is A, because intensity equals to your initial intensity into 1 minus e to the power minus k of t. E to the 1 minus e to the power minus kt, we used to have that equation in that fluorescence experiments and all. Now for IMSA also it remains the same. So intensity, the final intensity equals to your initial intensity into 1 minus e to the power minus k of t. So this is all. Okay, so that's all from my part. If you have any questions you can ask me, else we can stop the class over here. And this video is also being recorded, so you can actually listen to this lecture later in YouTube as well. So the NPTEL team would be sharing with you the slides and the video link as well. So I will be uploading them. And in any case of difficulties, you can contact me in my email ID. So I am writing my email ID. Okay, so you can contact me over here in case of difficulties. Okay. So I think that's all then. Okay. So thank you all. We will meet again in the next week. Okay. Thank you.